Okay. Hi everyone. First of all, I would like to thank the organizer for giving me the opportunity to contribute in this conference with my results. And also would like to thank all my collaborators for this work. I'm going to present basically the first interferometric survey in the K-band of massive XLR objects. And this was a work that got published last November. I also thank Aki for showing already how the disks surrounding protostars look like, so I don't have to give a lot of introduction. Yet I would like to take the opportunity for this slide already to give a bit of introduction. Why do we care about YSOs? Why do we want to study them in the K-band? And what are the main goals we want to achieve? Basically, massive stars, we know that they're very influential objects. We still have some issues to understand how they form. We know that disks are prominent in all kinds of star formation independent of the mass. Yet, the innermost regions of where the accretion takes place around massive XLR objects is unexplored. And we're talking about this region that basically the AU sub-AU scales, which are perfectly traced with the near-infrared dust continuum, but also with important diagnostic lines such hydrogen recombination line and the bracket gamma emission or the CO bandhead emission. So for the purpose of this study, we want to focus to this exact region where the accretion takes place, and we want to answer three very fundamental questions. First of all, are there small-scale disks surrounding YSOs? And if so, where is the inner rim of those disks located? Also, how does the ionization environment looks like in these subscales, sub-AU scales, AU scales? And we want to trace this ionization by bracket gamma emission. So basically, where is the bracket gamma emission located? Also, we know that the massive stars are found in binaries, especially when they are in the main sequence and more evolved phases, yet we don't know how they form. So another question we want to address is, do closed binaries that they have found at AU scales do already form at those scales, or is this something that happens later in the evolution? To answer these questions, we want to resolve and characterize the 2.2 micron hot continuum dust emission and its associated bracket gamma emission towards a sample of MYSOs, and also to provide the MYSO binary statistics at the separations of 2 to 300 AU, which is what we can trace with the instrument we used. We use a sample of 6 MYSOs of various luminosities, and this is the larger sample with homogeneous techniques, interferometric techniques in the K-band. The data we use are aberrant gravity on the VLTI, and the main method is geometric modeling. And here I show just an example of such geometric modeling towards one MYSO in our sample. This is what is called visibility curve, visibility over baseline. And basically, the data points are, the observations are white, the models are blue. And what I want to take to express out of this plot is that it depends on the shape of the visibility curve. One can set very important constraints on the brightness distribution of the sky. First of all, what is the size of your emission? Secondly, of what is the spatial distribution of the emission? This is something that is round in the sky, or is there some flattening going on? Also, if there are binaries, the interferometer should also be able to pick up the binary signatures. So answering the first question, where is the inner limb located? Basically, we apply these geometric models for the 2.2 micron condition, and we could extract the size of the continuum. And here I show a size luminosity diagram. Here is the ring radius over luminosity. The shaded areas are basically where the inner rim is predicted to be located from disk models. It doesn't matter at this point the specific of its model. And here is the area on the diagram where MYSO are located. This is the first time that we are able to place MYSOs in a size luminosity diagram. And the messages to take out of here is, here are T-Tauri, here are Herbigs. And I think there are two main messages we can take out. One is that it seems that it doesn't matter what is the central mass of your protostar. It doesn't matter if you are low mass, intermediate, or high mass. The inner regions of the disks around the protostars scale with the square root of the luminosity. And basically, with this, we extend the results presented from Milan Gabet in 2007 that was based on intermediate and loma stars. And another outcome from this plot as well is that indeed we can safely attribute the inner regions of, we can trace the innermost regions of the disk using the K-band measurements. Moving on to the second question, what is the size of the bracket gamma emission? Basically, again, apply the same similar geometrical models for the bracket gamma. And here I plot the radius of the bracket gamma over the continuum, over the luminosity. And what we can see is that for all YSOs in our sample, the bracket gamma seems to systematically originate from a region closer to the star compared to the dust. And this, in combination with some special information I could extract from the observations, that we found that basically not only the bracket gamma is smaller, but also that it's coplanar compared to the continuum. And this can hit towards a disk wind or base of the jet origin, as also can be demonstrated from this sketch here, which would be somewhere here. Going to the third question that we want to address, how about the MYSO binarity at AU scales? Well, it's not so high. So basically, we find only 1 out of 6 MYSOs to be parts of binaries. Here I plot the binary fraction over different phases of massive stars, of different evolutionary phases, embedded, which is this study through MYSOs. Pre-main sequence phase of young OBs, which were extracted from the gravity collaboration in 2008. And then we have the main sequence phase as well, OBs from Sun et al. 2014. Basically, from these two studies, I extracted the statistics for the 2 AU to 300 AU separations in order to be able to compare similar range of separations and scales. And what we find from this plot already is that it seems apparent that as the massive stars evolve, it seems to be also more observed in binaries compared to where they are younger. And another finding from this is that if we compare the binary fraction of MYSOs at those scales with what was reported back in 2019 from Pomohachi et al., who studied MYSO binaries at the larger scales from 600 to 10,000 AU and found about 30% of them to be binaries, is that for when we have to do with embedded MYSO phases, the binary fraction seems to be to follow a bit of flat binary distribution. And now I would like to summarize with, great, that was a bit faster. So I would like to summarize the conclusions. So we specially resolve the crucial star disk interface in the sample of MYSOs in the K-band. And we finally confirm the prominence of AU scale disks in high mass star formation. It doesn't matter what is the central mass of the protostar. The innermost areas of the disk seems to scale the size of the innermost area of the disk, scale with the square root of the stellar luminosity. The bracket gamma emission is overall more compact in size with respect to the thermal emitting dusty region, and the fact that they are also spatially aligned point to a disk wind disaccretion origin. And also, lastly, the observed fraction of MYSO binaries in K-band is almost flat for a wide range of separation between 2 to 10,000 of AU. While if you extract only the statistics between 2 to 300 AU separations, it seems to be seemingly less common MYSO binaries compared to massive main sequence stars on similar scales. And yeah, here is also the publication. And thank you very much. I'm happy to take questions.
Thank you very much for the talk, Evgenia. Very interesting one. If there are any questions on the audience here on Zoom, please raise your hand. Okay, Brian.
Yeah, thank you for the nice talk. So I'm not sure if this is a dumb question or not, but how exactly do you reconcile the fact that there are less massive YSO binaries, or if they're less common than massive main sequence stars?
So there are some things that we still need to consider here. So I think if it turns out to be the case, we have to consider how the binaries form. So one can distinguish between different binary formation theories and see if it's a tightening that happens later as the stars evolve instead of actually getting born at those separations already. That would be important if we confirm these results, though, because I have also to point out that with only a sample of 6 objects, although it's significant compared to what we knew years ago, or until this study actually, it's still a small number statistics. So we really have to look at the future and see what instruments we can use in order to increase this by at least an order of magnitude in order to be able to draw more safe conclusions if this trend is really there.
Okay, is there any other question? I have a quick question also regarding this binary issue. So I suppose when you said that you identify a binary, it means that you resolve it with your interferometric observations, right? So yeah. Is there any other information, for example, by spectroscopy, just telling you that perhaps you have a spectroscopic binary that you cannot resolve indeed with gravity or amber? And then, yeah, can you say something about it?
This is also a great question indeed. So spectroscopic binaries are a great way to observe and detect binaries at the sub-AU scales. So basically, one, in order to have a full picture of what's happening with binarity of YSOs, you have to go from spectroscopic binaries to interferometric binaries, and then to imaging binaries as well. And then you're going to be able to trace from sub-AU up to thousands of AU separations. In this kind of studies with interferometry, it's a bit tricky to support with spectroscopy, especially because you have to have a good diagnostic line in a specific regime of the spectrum. And usually the MYSOs are invisible in optical, for example. But also they are wide enough not to be able to observe within a few months. For example, you will need years and decades in order to be able to trace and in order to get enough data points in order to be able to construct radial velocity curves. No, it's an interesting question though, and I think it's something that we should work to combine information from multi-surveys and multi-techniques as well.